Good afternoon, everyone. A couple of words about me. I started networking back in the previous century, and I've been working with Cisco for about 12 years. So I worked in the escalation team in the TAC, doing security. Coincidentally, NATs. And a few years ago, I started doing as well IPv6. So now I moved into Network Operating Systems Technology Group. So today's talk is a little bit more than just the wireless experiences. So first, I looked at one of the tools that we have, and I looked at the IPv6 deployment in general in Poland. And I wanted to talk about the drivers for IPv6 deployment to begin with, right? So maybe some of you saw this webpage from the RIPE NCC, which said that basically we are out of IPv4 addresses. So we don't have any more IPv4 addresses left. And now every ISP can get only 1,000 more IPv4 addresses. So that means that practically whatever you have now of IPv4 addresses, that's something that you will have to live with. So there's no magic place to recover IPv4 addresses. So that's really that there is. And with that, we can take a look at where is the world with IPv6 deployment. So we have a tool which is publicly available at 6lab.cisco.com/stats, which allows you to look at various aspects of IPv6 deployment. So first thing that needs to happen before IPv6 can work successfully is IPv6 transit. So various countries are at various stages here. Well, I'm not sure if Poland is actually red in this case, but nonetheless, well, worldwide, internet transit is in reasonably good shape. So content is also in a pretty good shape, and the part that is so far a little bit missing is users. And it's also understanding, so as well, you can understand why, because deploying v6 to the users is probably the more complicated part of the equation. So, but why would you at all deploy IPv6 to the users? So, as the time went, we really forgot that once upon a time, the internet was end-to-end. So, restoring that is one of the incentives to have v6. So, really today, the users are sitting behind the network address translators, and as you will be forced to reuse IPv4 addresses more and more, they will be sitting behind the CGN. So full spectrum internet restoring end-to-end connectivity is one of the reasons to have IPv6. But as we talk about the CGNs, if you are an ISP, you will have to install them, and as you install the CGNs, they will create an ongoing cost. So that is not to say that, for example, Cisco doesn't have CGN. Well, every vendor has CGNs. So if you like to buy CGN, very welcome. Come, we will sell the CGNs. And we have very good, technically very good boxes. But the thing is that you will have an ongoing cost. So some things like logging, for example, auditing, and interaction with the law enforcement agencies, that's with the CGNs that is going to become more difficult. On the other hand, if you deploy IPv6 in parallel, then as more and more users start using IPv6, your cost of CGN will go down. So that's something to consider. Another thing, how many people in this room play World of Warcraft? Not that many. So nonetheless, the gaming is one of the other cases where you can as well move the users of the CGN. So the Blizzard Entertainment since June 6 this year made their games available on IPv6. So basically that's, again, one of the things where you wouldn't need to fight with the NATs to make the games working. So that is something to keep in mind. Now, that's all the service providers and consumers. So what about the enterprises? For the enterprises, one of the top drivers actually to deploy IPv6 is the bring your own device. So most of you probably carry your iPhone, and as you come to work, you connect that to wireless. So let's take a look at the practical experience. So IPv6 devices on wireless. So what are my personal experiences with that? I've been doing IPv6 on the Cisco events, well, for probably 3-4 years. And I'll just take a look at a couple of recent events. So one of the events was the IPv6 World Congress in Paris this year. So that was February. And I was measuring the statistics. So you see that we didn't have so many users. So we had, all in all, we just had about 600 MAC addresses with IPv4 address. But the interesting thing is that approximately 50% of them already had dual stack. Now, let's fast forward and take a look at the next event which I was involved in. That was Cisco Live in San Diego. So here the interesting thing is that the numbers are slightly different, right? So the number of users is in thousands, so it is probably one of the largest events with the dual stack network. And the more interesting thing is to start and compare those two tables relatively. So what is funny is that in less than half a year, the number of dual stack capable devices on the network grew from 47% to 77%. So that's pretty dramatic. And number of using IPv6, so out of those percentage that had dual stack, the percentage of devices that started to use IPv6 also increased. So mind you, here we had the Google IPv6, Google whitelisting on IPv6. So we already had pretty high usage. Now, the message that I'm trying to convey to you here is that with such a support on devices is something that you cannot ignore IPv6 anymore. And to take one example is a small test that I did yesterday evening. So I have this application on the iPhone which is called IPv6 workshop, and I did the ping to all host address. So I sent just 4 pings, and as a result I received 87 responses. So that means that a significant portion of the devices here at the conference was supporting IPv6, even though that we didn't have IPv6 on the wireless. So if we have the wireless that does not care about IPv6 at all, what are the potential problems there? So as you start learning the way IPv6 works, you see that it's really, in many regards, it's similar to IPv4. Some of the things are a little bit different. Some of the things are more renamed. So let's go over a few mechanisms. First thing that the device does when it connects to the network, it tries to discover the router. So it sends the router solicitation and tries to see if there is any router on the segment. So the router will send the router advertisement. So the attacker can basically send the router advertisement in parallel and try to make the client use the rogue router. So what does that entail? Well, that's something from just seeing the traffic from the user to full-blown man-in-the-middle attack. Now, one other part where we use router advertisement is so-called SLAC, so stateless address auto-configuration. So that is something that is new in IPv6, and this allows the host to configure the address based on the prefix it receives from the router. So then again, in this case, what can happen is that the rogue router can send the prefix, and it can force the host to configure the wrong IPv6 address. So again, in this case, the consequences can be very different. So realistically, these two attacks, they happen quite frequently, even though that they're not caused by the malicious intent, but primarily they're caused by the people who have the internet connection sharing on Windows turned on, and then they bring it in. So then their PC says, I'm a router, and it starts sending router advertisements. So the other devices on the network configure themselves with IPv6 address and start to talk IPv6 with this Windows host. So, and Windows host tries to do the connection sharing. And most of the time it works up until the point when this PC is removed from the network. So then obviously all the hosts get black holed. Now, can we do something more? Yes, we can. So we have also the address resolution, which is the function of the neighbor discovery protocol. So this attack is actually very similar to an IPv4 attack, which is done on the ARP level, right? So in the case of IPv6, we have different names for the messages, but the core of the attack is pretty much the same. So the host sends neighbor solicitation, and the attacker can try to pretend to be another host and to say, hey, well, that's me. But another thing that is new in IPv6 as a standard is the duplicate address detection. So every host, when it comes up, it tries to see if there is already this address on the network. So the host sends the neighbor solicitation. Is there anyone using the address that I'm trying to use, that I'm going to use? And in case we don't take any special measures, the attacker can again just reply to this message, yes, I'm already using this address. So, and then as hosts come up, they will all send neighbor solicitations, and the attacker can say, yes, 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 I'm using that address, and I'm using that address, and I'm using that address. So effectively, you can just take a single host, and with that host, you can just turn off IPv6 for all the new hosts that arrive to the network. So that's not fantastic. And that's why for wireless deployment in version 7.2, we introduced the features which take care of these attacks. So the router advertisement guard and the DHCP guard. These features ensure that the hosts cannot send the arrays, or they cannot become the DHCP server on the wireless side. So you know that your DHCP server and your router is on the wired side. So from the wireless side, it is not possible to perform this. The other part which helps with the spoofed addresses is the source guard. So basically, to ensure that all the hosts only use their own addresses, the wireless LAN controller or the switch needs to maintain a so-called binding table. So it needs to keep track who is using which address. And as part of that binding table, obviously we need to keep the addresses that are assigned to each client. So in this case, I'm just showing the screenshot from the wireless LAN controller in 7.2, where, yeah. So for the Flex Connect mode, I think we also support that, but we can verify afterwards. So we have the cache of the addresses per client on the wireless LAN controller. And of course, as well, for some of the features, we can run them directly on the access point. So that copy of the table is as well on the access points. So what we need to do is we, of course, need as well protect resources on the controller and on the access point. So we need to limit the size of this table to ensure that the host cannot just exhaust the memory on the central device. And in the wireless scenario, the size of the table was chosen to be 8 entries. So why 8? So normally you would have link local address and global address, right? So you would just have 2 addresses most of the time. Why 8? That's because there exists an RFC which describes the so-called temporary addresses. Why do we need temporary addresses at all? That's because people don't generally like to have the exact same lower part of V6 addresses as they move around. primarily because of the privacy reasons. Because if you keep the same interface identifier, then you become very easily trackable. So that's the origin of the RFC that described the temporary addresses, or so-called privacy addresses. And the lifetime of the address there, the preferred lifetime was 1 day, and the valid lifetime was 1 week. So that's how this address table size came alive. So you have 1 linked local address, and you have 7 temporary addresses, up to 7 temporary addresses, which can survive for a week. Now, realistically, not all the clients follow the exact way that it is described in the RFC. And some of the clients generate a new temporary IPv6 address each time they associate with this SID. So in the environments that I was involved in, that's a very, very dynamic environment. So that's a conference, right? So people associate to an SSID, people close the laptop, or people put the device to sleep, and then they move elsewhere. Then they, again, reconnect to the network. So that was a little bit challenging, I would say, thing, because you really have a conflict of interest in a way. Because you need to ensure that the addresses time out from the table as soon as possible, so you really want to decrease the timers. But then, on the other hand, as you decrease the timers, then you increase the amount of useless traffic on the network. So really, as the wireless LAN controller keeps the table up to date, it tries to verify the liveliness of the host using the neighbor discovery. So if you lower down the timers, then you create much more of this keep alive traffic. So as a result, well, we used lower prefixes that are there by default. So it worked. I think I've heard positive feedback about that, but that is very chatty. So as a result of this client behavior, we changed in the new version. In the 7.3, normally the algorithm with which we maintain the table will be different. So as the table gets to full state, then the controller will start to aggressively time out the older entries. Now with 7.2, there is not a lot of magical solution. If you want to have less traffic, then the simpler approach is just to use the stateful DHCPv6 and then to give out the addresses. Of course, that will, in some cases, limit the number of clients, number of operating systems that you can connect to the network. Now, that's all great, but we're talking dual stack. So we need to continue to provide v4 as well. And that's kind of a baseline that everyone keeps in mind. But as soon as we start to do dual stack, the behavior of the clients changes, right? So now you need to take care about the interaction of the two address families. And depending on the operating system, that behavior might be different. But the nutshell is that you need to have both protocols running. So effectively, your costs, so your administrative cost will be higher than just with a single protocol family. So, and as Ron mentioned yesterday, well, really, as you run dual stack networks, you really start to think, well, so how can I really try to turn off v4 and see what happens? So the question is, okay, so that's all great, we run dual stack, but can we try to go v6 only? So how can we do that? One of the technologies that we used is NAT64. So the idea is that we have clients which are v6 only, and then for the servers which are dual stack, they will use IPv6 because there's no IPv4 on the client side. For the servers that are IPv4 only, we will then pass through the stateful NAT64, which will translate IPv6 on the client side into IPv4 on the server side. So really, NAT64 stateful is used to connect the IPv6 cloud to IPv4 cloud. Why do we need the state in this case? We need the state because if you are coming from the IPv6 side of the internet, when we get to IPv4 side, the addresses become smaller. So there is really nowhere to store this information, who exactly from the IPv6 side is coming to IPv4 side. So that's why you need to keep a state in this gateway device. If we look at the packet flow in a little bit more detail, so we have this client in the internet which sends the packet. So it sends the packet to a special IPv6 destination. So this destination is consisting of NAT64 prefix, and well, last 4 bytes will be the same as IPv4 address of the server. Once the packet reaches the NAT64 device, we create the entry. We create the state for this connection. So, and in this state, we take this address, and that becomes the destination IPv4 address. And then we take the pool from the configuration and hide the source address behind the v4 address from that pool. So then on the exit from here, we can send the packet to v4 server, and it will look like a normal v4 packet. So the server will not know that the client is talking IPv6 with it. As the server replies, we can hit this entry, we can hit the translation entry, and we can do the reverse transformation. So we can send the packet back to IPv6-only client, and it will think that it talks to IPv6-only server. So that's all great, but who will fix the addressing for us? So the sites that are v4 only, they are v4 only for a reason. So they don't have the v6 address. So in order to do that, we use the DNS64. That's a second component of the solution in this case, which allows us to create these synthetic IPv6 entries. So if you are interested to experiment, it has been implemented in Bind, which is probably one of the most widely used systems DNS-wise. And let's take a look how exactly it works. So if we're talking about the host that has the quad A record, so the host that has IPv6 address, then as we configured the prefix for NAT64, the client sends the query. So the client asks for the quad A record of the example.com site. Then the DNS64, in this case the bind, it will act pretty much exactly in the same way as it does without the DNS64. So it will ask for the quad A to the authoritative server. The authoritative server will reply, and then it will forward the reply back to the client. And as I said, it will be exactly the same as in the normal DNS case. So the interesting things start when we do not have the quad A. So the host starts again with the same question, and our DNS64 asks the authoritative name server, so what is the IPv6 address? The server says, no, we don't do that here. So what we do then is that we say, okay, well, at least give us the IPv4 address. So then comes back the IPv4 address, which gets inserted using this configured NAT64 prefix into the synthesized answer. So then this DNS server can return this IPv6 address to the client. So, and then the client can take that synthesized IPv6 address and connect towards the NAT64. So just a simple example of how this looks like on the SR1 case. So the configuration, as you see, is very short. And basically the elements are somewhat familiar to the elements that you have when you configure the v4 NAT. So, and this is the config that we ran at about 3 or 4 events, I think, where we had an SSID which was dedicated for IPv6 only, and that SSID had the DNS64 and NAT64 combination used to access the v4 only websites. So what does work and what doesn't work in this scenario? So we found that really a lot of things work. Quite some applications work. Everyday browsing works quite well. And, well, most of the desktop operating systems work fine, so especially the latest ones. So some fraction of the applications doesn't work. So in 85 and 15, that's rough estimate. So that was done by Cameron Byrne from US, who was doing very extensive testing. So we, in our experiments, we didn't do such an extensive testing. We just used kind of more the user feedback to get a feel of what works, what doesn't work. So Skype and various other chat and multimedia programs have a little bit of a hard time working. So you really need to search specific apps to ensure that they work in v6-only environment. So all in all, the conclusions from this experiment were that, well, we do still need to have v4. So v6-only is more something that we need to keep trying, because otherwise we will never get to that stage. And remember that dual stack, as you deploy it, that's only part of the journey, right? So the real final end goal is to have the internet on v6. Something that I think Ron already told yesterday, that as you put the devices on v6-only network, then they don't see any DHCP v4 servers anymore. So they assign the link local IPv4 addresses. They assign the plug-and-play IPv4 addresses. And the RFC says that, if you have this address and you need to talk to some v4 address on the internet, then you can just do the proxy ARP. So that's created quite a significant amount of traffic on the wireless LAN. So we solved that by putting the fake DHCP v4 server and just effectively giving the v4 address but blocking it on the first hop. So that's kind of a temporary hack, I would say. So that's something that will need to be fixed. One part that was fairly tricky was the mobile clients. So as I said, the laptops, the desktops are fairly straightforward. So most desktop operating systems work in IPv6-only mode. With the mobile clients, the situation is a little bit more challenging. So for example, iOS in versions prior to 6 had a little bit funny behavior UI-wise. So you would get connected to IPv6-only network and you would have the connectivity, but the icon would not light up. And on some iPhones, it would also periodically disconnect. So iOS 6 has fixed those problems, but then there were a few applications that broke during the upgrade. So really, the apps on mobile operating systems need testing as you perform the OS upgrades, because really it's not a given that something that was working before will work in the future. So my personal understanding is that maybe it is still that some of the development probably needs to include more of IPv6 testing and more of IPv6 API. The other part, which was a little bit difficult, was the DHCP v6 support. So I mentioned that on one hand, Slack is a very interesting and theoretically scalable mechanism. On the other hand, it allows the host effectively to self-assign whatever address they choose. So overall, that creates a concern and a headache for the administrators. But some of the devices don't support DHCP v6. So if you run with stateful DHCP v6, then you effectively cut those devices off the network. And some of the devices don't support even stateless DHCP v6, so you cannot run them in v6-only mode at all. So, but as we see over time, the situation is slowly improving. So I would say probably we should revisit this in half a year, and see what the next generation of the operating systems on the client will bring. So basically, we still need IPv4. And now I will put a little bit of a service provider hat on and say, hey, well, so how can we minimize the headache? So really today, the way you give IPv4 to clients is to run CGN, or if you're a little bit more adventurous and you look to run on top of v6 transport, this is DS Lite. However, well, if I look at it from the architecture standpoint, and I put deliberately the comment here that NAT is a fairly very wide term in here, so I use it liberally just because it was very short and easy to put in the circle. So in both scenarios, you have a big box with a lot of state in the center of the network. So as your homes start to connect to the internet, you need to keep the state here. So much like I had NAT64 box keeping state, you need to keep the state on the CGN or DS Lite box. And by the way, well, the big difference with NAT64 is with NAT64, your investment will be, so your expenses will be normally gradually going down. Whereas with CGNs, as you keep more and more clients, you will need to maintain more and more of these boxes. So this means also the challenges from the scalability standpoint, right? Because you have only one box which concentrates all of the state, then you cannot really put another one and route traffic asymmetrically. That's a bit challenging. You probably can do that, but it's a bit tough. So what can we do? If we go back a little bit to the network, to the way the networks are designed, we generally have some sort of aggregation, right? So we have the upstream links, and then we split the network. So we, let's take a look at IPv6, right? So we, for example, allocate 2001 DB8:32 to this SP network, and then to each of the households, we allocate /48. So, and I take the numbers just purely because the addresses are fairly short. So in reality, they can be, of course, different. So we allocated them this way, and 2001 DB8 is basically the network that we have overall. And then the third number will be the so-called household number. So we can take prefix and call this part embedded address. And this is the space for the subnets and the home, and this will be the interface ID. So that's how we can kind of chop IPv6 address. So what is interesting about that? This is something that is exactly the same for all the CPEs, right? So that is then becomes part of the static configuration. This part is unique per CPE, and that's basically the provisioning on the CPE that we can do. This part, we don't care about. But what we can do is now we can use that to take the IPv4 prefix and take 8 bits of this and say that, hey, for this CPE, that's how you derive the IPv4 address. So that's all great, right? Because I don't need to store the state, and I can now kind of, based by formula, figure out who has which address. And if you note, well, in this case, I now have 256 CPEs using the same IPv4 address. So how comes? This is where we play another trick. And we pretend that ports are part of our address space. So it's a little bit weird thing to think a little in the beginning, but if you keep in mind that we allocate the public ports, that becomes fairly interesting. So in this case, we give a fairly, well, we are fairly aggressive because we give each of the CPEs just 256 ports. So that's probably something that would need to be tweaked in reality. But that's just for having the numbers simple to operate with. So if we use this approach, what becomes possible? It becomes possible to get rid of the state on the big boxes in the core and to move the state back to the CPEs where we have it now. So then as the hosts on the inside start to talk to something on the internet, The CPE can translate the RFC 1918 address into the public address that it has, and it can pick the public port out of the port range that it was assigned during the provisioning. So then it would somehow put the packet into IPv6 and send it towards the border router. So border router then, because it knows the source IPv6 address, it can, based on formula, it can verify that the port is correct. And it can then do the operation where it will transform the packet into v4 address and send it towards the server. So the server sends the reply, and the reply can go to a different box here. So note that compared to the stateful operation, we don't keep any state here, so we just keep the rules by which we translate the address. So we can, knowing the destination v4 address and the port, we know which of the CPEs that port group belongs to. So we can encapsulate the packet back into IPv6, and we can send it back to the CPE. So then the CPE will perform the reverse translation and then undo the not44 function that it was doing. So with this approach, you can scale much, much, much better. And what's nicer, the state that is kept otherwise in the central box becomes distributed to the CPE. So then you get roughly the similar situation as you have today, except your IPv4 address is shared between multiple CPEs. So more information about this, and I deliberately didn't talk too much about this approach, so it's called MAP, mapping address and port. You can find in the ITF draft, and also we have a tool which I will do a short demo with. So basically, we have the IPv6 addressing, and we can play with various bits, and we can play with the prefixes that we allocate. And then we can see, so how many users can we serve with the given number of IPv4 addresses. So if we take, for example, the /23, so we take the last allocation from RIPE, and we take half of it, then we can see that we can, depending on the how we move around the EA bits, we can have more or less users with different ports. So for example, this is a fairly good allocation, right? So we have almost 1,000 ports per user, and with just 512 IPv4 addresses, we can serve 32,000 users. So that is a fairly good amplification. And again, all of this is something that you can do without keeping the state on the central box. So this technology, the way you encapsulate the traffic in IPv6 is twofold. So there is two flavors of this. One is called MAP-E, so that's encapsulation, and that is going currently in IETF standards track. The second is MAP-T, where you use translation in order to transport this IPv4 client traffic across your cloud in the ISP. So that one is in the experimental track. And in the upcoming ITF, there will be interop, in which various vendors will test the compatibility of this technology. So it's not just something that is written in the standards alone. So there is a running code already, which, if you're interested, then get in touch with me, and we'll see. So I think with this, that's all that I had, and I will be very happy to answer your questions.